Hi students, this is our second video for the topic of integration for the International Baccalaureate course Analysis and Approaches. In this video we're going to look at methods of integration. We're going to start by looking at substitution, which is applicable for SL and HL. Then we'll move on to partial fractions and integration by parts, both of which are in the high-level syllabus. Now, we touched on the reverse chain rule last lesson, but now we're going to look at it when we have a composite function. So when we have a composite function that we want to integrate, if we have the derivative of the inside function sitting here, ready to be cancelled out, then this integral will equal the antiderivative of the outside function plus c. Here's an example. You can see we have a composite function here. The inside function is x squared. The derivative of x squared is 2x. So this is just equal to the antiderivative of the outside function, which is an exponential, and that doesn't change. So our answer is e to the x squared plus c. Now some students will do it like this. It's not the most elegant of methods, but it kind of makes sense to them. So integral of 2x e to the x squared dx. We recognize that this is the derivative of the inside function, and we just leave it alone. Now we go about doing the reverse chain rule on e to the x squared. Outside function is an exponential, so it stays the same. Divide by the derivative of the inside function, which is 2x, and these cancel out. Now, providing the x part cancels out and we're not introducing a new variable, this is valid. So it's equal to e to the x squared plus c. But there is another way. We can make a substitution. Typically, we are going to substitute for the inside function. So the inside function in this case is x squared, and we're going to let u equal x squared. Now, somewhere on your paper, you're going to make these notes. Let u equal x squared. We need to find du dx, which is 2x. Now I'm going to split up this derivative and write du is equal to 2x dx. And I'm ready to substitute in. I've got 2x dx there, that's going to become du, and e to the x squared, that's going to become e to the u. Now be careful of your order, because this isn't right. Du always has to go at the end, like this. But now, look how easy this integral is. The integral of e to the u du is e to the u plus c. Now don't stop here, you have to substitute back. So instead of u, we want to write x squared. Example 2. By making the substitution u equals 2x squared minus 1, find the integral of x multiplied by 2x squared minus 1, or cubed dx. Right on the side of your page, we're writing let u equal 2x squared minus 1. Du dx is equal to 4x. Splitting that derivative, du is equal to 4x dx, which doesn't quite match because I don't have a 4 here. So let's just take that 4 over this side of the equation. So du over 4 is equal to x dx. We're ready to substitute. This is going to become u cubed, and x dx will be a quarter of du. Now we're going to integrate. This will become u to the power of 4 divided by 4, and tidying that up and substituting back, we have 2x squared minus 1 to the power of 4 over 16 plus c. We can use substitution with trig integrals as well. And this is actually how we find the integral of tan x, because tan x is equal to sine x over cos x. We're going to use the substitution u is equal to cos x. So on the side of our page, let u equal cos x. Du dx is equal to negative sine x. Splitting that derivative, du is equal to negative sine x dx. We've got positive here, so let's multiply both sides by -1, and we're ready to substitute. So instead of sine x dx, we're going to write negative du, and instead of cos x, we're going to write u. This is a log base e, so it's going to be negative ln u plus c, and then substitute back, we have negative ln cos x plus c. And let's do one more. This one's slightly different. Use the substitution u is equal to x plus 1 to find the integral of x multiplied by the square root of x plus 1 dx. It's different because we don't have the derivative of this inside function sitting here. But this is going to work because it's going to break down this square root. I'll show you what I mean. Let u equal x plus 1. Therefore, du dx is equal to 1. Du is equal to dx. So that's going to be a straight swap. This is going to be the square root of u. But what is this going to be? We need to rearrange this equation and make x the subject. So x is equal to u minus 1. Let's substitute in. Can you see how we've broken down that square root? I couldn't do anything with it like this. But now I can expand these brackets. So we end up with u square root of u minus the square root of u du. Let's go into index form, and we're ready to integrate. Now this question does become a little cumbersome because of the fractions, but you just need to practice. If we're going to integrate this, we're going to raise the power by 1, which is 5 halves, and then divide by 5 halves. Here we're going to raise a half by 1, that becomes 3 halves, and then divide by 3 halves. Now this is just a reciprocal, it's 1 divided by 5 halves, so that's 2/5. So we just flip it up, and 1 divided by 3 halves is 2/3. So I'm going to flip those fractions up, and I'm going to substitute back at the same time. And there's our answer. Here's a past exam question. Part A, find the integral of x e to the x squared minus 1 dx. We can do this through the reverse chain rule, or we can use substitution. I'm going to do substitution because we just learnt that. It doesn't tell us what to substitute, but as a general rule, we are looking for this inside function, which in this case is x squared minus 1. So I'm going to let u equal x squared minus 1. Du dx is equal to 2x. I don't have a 2 here. I've got x dx, so I want du over 2 equals x dx. We're ready to substitute. So it's going to become e to the u over 2 du. Let's just have a look at that. The x dx became du over 2, and the e to the x squared minus 1 became e to the u. All right, really easy to integrate. We have e to the u over 2 plus c, and substitute back. We have our answer. B, find f of x given f dashed of x is equal to x e to the x squared minus 1, and f of negative 1 is equal to 3. So we're given the derivative. We want to find f of x and then resolve the constant. Now in part A, we found the integral of this. It was e to the x squared minus 1 all over 2 plus c. Let's substitute in x is equal to negative 1 and f of x is equal to 3. Tidying that up, c is equal to 5 over 2. Therefore, f of x is equal to e to the x squared minus 1 plus 5 all over 2. Okay, let's move on. We're going to look at odd powers of sine and cos because these can be done through substitution as well. But there's an extra step. Here we've got the integral of sine to the power of 5x dx. I'm going to strip off one of those sine x terms. So we're going to write it as sine x multiplied by sine to the power of 4x dx. Now sine to the power of 4x, of course, is sine squared x all squared. And I can write sine squared x as 1 minus cos squared x. Expanding those brackets out and then separating into 3 terms. I have the integral of sine x, take away 2 sine x cos squared x plus sine x cos to the power of 4x dx. Now one thing you can do with integration is if you get a really complicated integral like this, you can split it up and then deal with each one in turn. This one's easy. This is just negative cos x. Both of these will require substitution or using the reverse chain rule. And your substitution would be u is equal to cos x in both cases. I'm not going to work through that because we've done enough of it, but I encourage you to. Here's the answer. Negative cos x plus 2 cos cubed x on 3 minus cos to the power of 5x on 5 plus c. Now you're probably thinking, well, what about even powers of sine and cos? And I'm going to cover those now, but we don't use the same method that we use for odd powers. In particular, we're not going to strip off a sine x and then use a substitution. Instead, we're going to recognize that sine to the power of 4x is the same as sine squared x all squared. And I'm going to use a trig identity. We're going to use cos 2 theta. Now, in your formula booklet, you get 3 versions of this. And I want this last one, the one involving sine squared theta. I'm going to take cos 2 theta equals 1 minus 2 sine squared theta, rearrange it, and make sine squared theta the subject. And now let's substitute that in here. And we're going to expand that out. I'm going to take this quarter out the front. And we have the integral of 1 minus 2 cos 2x plus cos squared 2x dx. This is fine, this is fine, this is cos squared 2x. We need to do the same thing again. But this time, I'm going to use that part, the one involving cos squared theta. So take cos 2 theta equals 2 cos squared theta minus 1. Rearrange and make cos squared theta the subject. There's a subtle difference here. We have got 2x instead of x, but that's okay. Cos squared 2x will equal half cos 4x plus 1. So let's substitute that in. Now I'll always encourage you to tidy an integral up before you integrate, so let's expand these brackets and collect like terms. Alright, now we're ready to integrate. This is easy to integrate because we no longer have the powers involved. So this is just going to be, this is a reverse chain rule, but I'm not going to use substitution. So the outside function is cos, the inside function is 4x. So we're going to end up with sine 4x divided by the derivative of the inside function, which is 4. And very similar here. And just tidying that all up, we end up with sine 4x over 16 minus sine 2x over 4 plus 3x over 8 plus c. Now there are other types of trig substitutions that you can do, like this question. Find the integral of the square root of 4 minus x squared dx by making the substitution x equals 2 sine u. Now you can see it's a little bit different to what we've been doing. Normally we've substituted u equals some sort of function of x. But we're going to do the same method. We're going to let x equal 2 sine u, find dx du, and then split that derivative. So instead of dx, we're going to write 2 cos u du, and instead of the square root of 4 minus x squared, we're going to substitute x is equal to 2 sine u. So let's substitute in. Factorizing here, we're going to get 4 outside of 1 minus sine squared u, which of course is equal to cos squared u. And taking the square root here, we're going to end up with 2 cos u times 2 cos u du. Tidying that up, we end up with 4 times the integral of cos squared u du. And just like before, we're going to use the double angle formula for cos, rearrange it so that cos squared u is the subject, and substitute in. And now we're ready to integrate. This is 2, and then we have u plus sine 2u divided by 2 plus c. And now we need to substitute back, and this is quite tricky. So remember that x is equal to 2 sine u. We want to know what u is equal to. So dividing both sides by 2, we get x on 2 is equal to sine u, and so u is equal to arc sine of x on 2. So that one's done. But what on earth is sine 2u? Let's use the double angle formula. And we know that 2 sine u is equal to x, so that part's okay. For cos u, we're going to draw up a right angled triangle. Here's our angle u. So sine u will be opposite over hypotenuse. And using Pythagoras' theorem, we end up with the adjacent side being equal to the square root of 4 minus x squared. So cos u is adjacent over hypotenuse. So let's see if we can put this all together. 2u is going to be 2 arcsine x over 2, and then sine 2u is x times the square root of 4 minus x squared all over 2 plus c. Okay, that's it for substitution. Let's move on to partial fractions. Now from this point on in the video, it's for HL students. When we have multiple binomial or trinomial factors on the denominator, we can use partial fractions methods to separate them. So you can see here we have got two linear factors and we can't actually integrate this. But when we write it as partial fractions, we can. Now we learnt partial fractions methods in Year 11, but let's revise them. Example 1, write 2 over x squared minus 1 in the form a over x minus 1 plus b over x plus 1. So you can see how we got there. This is x minus 1 multiplied by x plus 1. So we're just going to let those two be equal, and then I'm going to make a common denominator here. And I can equate the numerators. 2 must be equivalent to a multiplied by x plus 1 plus b multiplied by x minus 1. Now we're going to make strategic substitutions to eliminate variables. We'll start by letting x equal negative 1, because that's going to wipe this whole term out. We end up with 2 is equal to b multiplied by negative 2. So b is equal to negative 1. Now we're going to substitute x is equal to 1. And we'll end up with 2 is equal to 2a, and so a is equal to 1. Therefore, we can write 1 over x squared minus 1 as 1 over x minus 1, take away 1 over x plus 1. Hence find the integral of 1 over x squared minus 1 dx. So let's use our partial fractions decomposition. And now we can integrate. So this is going to be log base e, and so is this. And we can join those together using our second log law. This becomes ln, or log base e, of x minus 1 over x plus 1 plus c. Now there are other types. The question we just did was linear factors. When we have a quadratic factor, we put bx plus c on top. It's possible that b or c might end up being 0, but we won't know until we try. The other type is a repeated linear factor. And in addition to having this term, we're going to have the linear factor by itself. Again, b could end up being 0, but we won't know until we've gone through the process. One more rule. We can't use this method of partial fractions when the degree of the numerator is equal to or higher than the degree of the denominator. And we're going to look at a question like that later on. So we're going to look at an example that has a quadratic factor on the denominator. So we're going to let 2x squared plus x plus 1 all over x squared plus 1 multiplied by x minus 1 equal ax plus b over x squared plus 1 plus c over x minus 1. Making common denominator here, I have just equated the numerators, so I'm working a little bit more efficiently. You can put an extra step in there if you want to. But 2x squared plus x plus 1 must be equivalent to ax plus b times x minus 1 plus c times x squared plus 1. Right, we're going to start by letting x equal 1. So that's going to wipe out all of this, and we'll be able to solve for c. So putting the 1 in there, we get 4 is equal to 2c, so c must equal 2. Next, we're going to let x equal 0, and wipe out this term here. We're going to do 1 is equal to negative b plus c, and c is 2. So b is equal to 1. And then finally, we're just going to choose another x value. Let's choose x equals -1. And we're trying to solve for a. So substituting in and solving, a is equal to 0. So we have no term in x on the numerator here. And now we're ready to integrate. So this is arctan, and this is log base e. So the answer is arctan x plus 2 log base e of x minus 1 plus c. Example 3. Show that 3x plus 5 all over x plus 2 multiplied by x plus 1 all squared can be written as 1 over x plus 1 plus 2 over x plus 1 all squared minus 1 over x plus 2. Now you can see this is a repeated linear factor, and we do have a term that has x plus 1 all squared on the denominator, and we've also got one that has x plus 2. Now you can use partial fractions methods to prove this, but you can do it in reverse because it hasn't suggested a method. We could just make this into a common denominator and prove that it equals this. And that's much easier, so let's do that. So start on this side. Common denominator is going to be x plus 1 all squared multiplied by x plus 2. This term here is missing an x plus 1 and an x plus 2, so put that on the numerator. This one is missing an x plus 2. And this one is missing an x plus 1 all squared. Right, we need to expand that numerator out and tidy it up, and we get our answer. But there's more. Hence, evaluate the integral of 3x plus 5 all over x plus 2 multiplied by x plus 1 all squared. So here's the partial fractions decomposition. This is log base e. This is a power rule. This is x plus 1 to the power of -2 if we lift it up the top. And there's another log base e. All right, we're ready to integrate. We have log base e of x plus 1 plus 2. Remember, this was x plus 1 to the power of -2, so raise the power to -1, divide by the new power, divide by the derivative of the inside function, but that is just 1. Take away log base e of x plus 2. Let's tidy it up and join those log terms together. We have log base e of x plus 1 over x plus 2 minus 2 over x plus 1 plus c. Now I mentioned before the degree of the numerator. If the degree of the numerator is equal to or greater than the degree of the denominator, the partial fractions methods we've used won't work. So for example, x squared minus 15 over x squared minus 9 is never going to be equal to a over x minus 3 plus b over x plus 3, because you can't get an x squared term out of that. So what we need to do is reduce it. Now this one's a really easy one to reduce. I'm going to match the denominator, x squared minus 9, and steal that from the numerator like this. So instead of x squared minus 15, I'm writing x squared minus 9 minus 6, that's still the same. And now I'm splitting this up, and it becomes 1 minus 6 on x squared minus 9, and now I can use partial fractions. So it'll end up looking like this. Now that was a pretty easy question. What if we get a more difficult one like this? You can actually use the same method. It will work. But you could also use long division. So divide x squared minus 9 into x squared plus x minus 15. This fraction will be equal to 1 plus x minus 6, the remainder, over x squared minus 9. And we have successfully reduced the degree of the numerator. And we would continue from here using partial fractions methods. Or you could set up an expression for what you need. You could rewrite this as some constant plus bx plus c over x squared minus 9. See, a lesser degree than the denominator. And you're probably way ahead of me, because you could also do it like this and do it all in one go. Okay, last thing for this lesson, I promise. Really useful technique called integration by parts. Now, I mentioned last lesson that we don't have a quotient rule for integration. We have a limited chain rule, the reverse chain rule, and we don't have a product rule. This is as close as we get to a product rule. There's the formula, you can see that on the screen. It actually comes from the product rule, which is the derivative with respect to x of u times v is uv dashed plus v u dashed. Now rearranging that and making uv dashed the subject, and then taking integrals of everything with respect to x, we end up with our integration by parts rule. Now, as you are learning integration, you're going to get a lot of different methods, and you've got to learn to pick which method to use at which time. So when we're doing integration by parts, we're looking probably for a product, and it will be a mixture of algebraic, trigonometric, logarithmic, or exponential parts, like the two that you can see on the screen. So here's the method. We split the integrand into two parts. One part's going to be equal to u, and we will differentiate it. The other part's going to be equal to v dashed, and we'll integrate it. It's really important to choose carefully, otherwise you end up making the integrand more complicated. Here's our first example. Find the integral of x e to the x. You can see substitution is not a viable method because we've got nothing to substitute. This is not a composite function. So this is where I want you to start considering that integration by parts might be an option. We're going to let u equal x, because when I differentiate that, it'll become 1. And of course, v dashed equaling e to the x, when I integrate e to the x, I get e to the x. So that's going to be u, and this is going to be v dashed. So we set it up like this. Differentiating, we get 1. Integrating, we get e to the x. You don't need to worry about the constant at this point. Now, using our formula, it's going to equal u times v, so u times v, take away the integral of u dashed times v. And see, we've reduced this to this, which I can integrate. And now we put the plus c in right at the end. And there's the answer. Now there's this funny little acronym, LEATE, which can help you with choosing which function is going to be u. And remember, u is the one that we differentiate. So top of the list, if there's a log function, that's going to be u. Next is inverse trig functions like arc sine. Algebraic functions like x or x squared, then trig functions, and bottom of the list is exponential functions. Now I have to say, this is not set in stone. There will be some times when you will break this rule, but generally it can be helpful. Here's example 2. Find the integral of log base e of x dx. Now you're probably thinking, how can we do that? We've only got one function. We don't have a product. So there's a sneaky trick to this. We're going to rewrite this as 1 times log base e of x dx. You're going to use a very similar method if you want to integrate any of the inverse trig functions like arc cos, arc tan, and arc sine. Now we have a product. Using our LEATE rule, u is going to be log base e of x. And so that means v dashed will be 1. Let's differentiate log base e of x and integrate 1. Now let's construct integration by parts. We have got u times v, take away the integral of u dashed times v, which is 1. How nice is that? So our answer is x log base e of x, take away x plus c. Now sometimes we need to apply integration by parts more than once. In this first example, if we choose u to be x squared, the first time we do integration by parts, that'll reduce to an x. And then if we do it again, it'll reduce to an x to the naught, which is 1. And we'll be able to integrate the trig term that remains. This is another example, but not immediately obvious, so we're going to have a look at that question next. Is integration by parts to find the integral of e to the x cos x dx. So our first job is to decide what is u and what is v dashed. from our Liate rule, exponential's right at the bottom of the list. So we're going to make cos x u, and e to the x will be v dashed. Differentiating cos x and integrating e to the x, and using integration by parts, we end up with this. And we haven't really got anywhere. We've just switched to cos x for a sine x. So we're going to do it again. Now the basic rule is when you use repeated integration by parts is stick with the same method. If you made the trig function u, then the next time make the trig function u. So we're going to let u equal sine x and v dashed equal e to the x. Differentiating sine x, integrating e to the x, and using integration by parts, we end up here. And now we're back where we started, which is going to help me find the answer. Because we've ended up where we started, these terms are the same, and I can join them together. So I'm really going to solve an equation. I'm going to take this over the other side, and then divide both sides by 2, and there's our answer. Okay, that's it for this lesson. Now, a lot of content in it, and you need to go and hit the books and do some practice. Our next lesson is on the fundamental theorem of calculus.